Okay, by now you've watched this video clip, this demo of the wire in the horseshoe magnet. I didn't do a lot of talking in that video, so I'm gonna explain what you saw. But first, what I wanted to start to get you excited about all this is that little experiment that you saw leads to so much. Um, the theory behind it, I said, okay, engineers could take over. I'm going to give you the basic theory in class, but what the engineers led to is they led to every single wireless communication. So think of where we're at today with how many things are wireless. Your cell phones, your Wi-Fi, even if we go old like AM, FM radio, satellite radio, GPS signals, anything with a wireless aspect to it is rooted, its technology is rooted in field theory. We wouldn't have it today if earlier scientists hadn't figured it out, this field theory and this deep connection between electricity and magnetism. What we saw in the video, usually a charge just creates an electric field. But what we saw a force. And if I can backtrack to that summary we did earlier, the only way we'd get a gravitational force is if there were two masses and their gravity field overlapped. The only way we'd get an electric force is if there are two charged objects and their electric fields overlapped. The only way we'd get a magnetic force if there's two magnetic fields and those magnetic fields overlapped. The force we saw on that wire, obviously it's not gravity. Gravity didn't make that wire get pushed out of the horseshoe magnet. You might think that it's electricity because there's electricity flowing through the wire, but it turns out it's not an electric force. We could do another experiment, maybe ground the horseshoe magnet so that it didn't have any charge built up. So the only possible outcome is it's not gravity, it's not electricity. That means that the force must be magnetic. So there's a force on the wire, it's pushed out of the magnetic field due to a magnetic force. The only way there can be a magnetic force is if there's two magnetic fields. The only way there can be two magnetic fields is if that current in the wire created its own magnetic field. So that's kind of a long runaround for a very important thing. Electric currents create magnetism. We're going to call that electromagnetism, very clever name. If you had something with a lot of charge, like static electricity from grade 9, maybe that big ball that teachers sometimes bring in that makes people's hair stand up, if you just have a whole bunch of charge, but the charge isn't moving, then that charge doesn't have any magnetic properties. But if you have some charge and you, with a battery, or in that video I used like an electric battery pack, if you use a battery to push charge around, once the charge is moving, moving charge creates its own magnetism. That is huge. We can use electricity to make magnetism. What we'll circle back to in grade 12 is it's symmetrical. If we can use electricity to make magnetism, we can use magnets to make electricity. That's our whole power grid in North America. The tumbling energy of Niagara Falls spins some magnets. Those moving magnets make electricity. We send the electricity down wires into our houses. We're going to say that for grade 12, but the flip-flop of that is magnets can make electricity. What we're going to look at today is electricity can make magnetism. We're going to call it electromagnetism. It's a huge deal. We now have the ability to make magnets. Magnets are in things like motors and all sorts of devices, speakers, the earbuds you might be using. So the fact that we can make our own magnet means we can engineer really cool, strong things, really cool, small things, all because now we don't have to rely on these special metals as magnets. We can make our own. Okay, so the short-term focus is we need to figure out electromagnetism. Oh, sorry, there's more blurb here, bad page break, so skim through that. Just know that this is something we should be excited about, and early scientists were very excited about this, the fact that they could use electricity to make a magnet. We're going to split electromagnetism into two parts. The first one we're going to do is we're going to consider the electromagnetism, so the magnetic field created by electricity flowing. That's what electromagnetism is. If the shape of the wire is just sort of a long, straight, kind of boring wire. So I've typed it all out here. Read through it slowly. I'm obviously talking through it with you as well. It is a little bit weird to learn online, but I think with the audio of this, me talking through this video and with this whole bunch of stuff I've typed, hopefully it'll click. We know, well, hopefully we now know, that when we have a charge moving through a long straight wire, that moving electricity is going to make a magnetic field that exists around the wire. Sometimes people get confused, so I want to emphasize this. Technically, even though there's charge moving through a wire, the wire is neutral. There's protons and electrons in it. There's the same amount. It just happens that the electrons are moving. So we don't have to worry about an electric field because it's a neutral object. We only get electric field from charged objects. Since this thing's neutral, no electric field to worry about. We've tried to do this one in class in a lab, and it's really tricky to set up. So even if we were in school, I wouldn't technically really do this as a lab. But here's what I'm going to tell you, and you're going to have to kind of trust me. If we push charge through a long straight wire, so a battery make electricity flow through a long straight wire, we get a magnetic field around the wire, and it happens that the magnetic field happens to be in circles around the wire. So remember way back when we started all this, we were talking about vector fields, that cool picture of the wind. If we could picture the magnetic field as that kind of diagram, a whole bunch of arrows, the arrows would be circular around the wire. That's kind of the goal of grade 11, is that we're just going to figure out the direction of the magnetic fields, for now straight wires, and then we're going to switch it a little bit later. So you're going to have to kind of trust me for now, but if we ran electricity through a straight wire, we get a magnetic field that's circular around the wire. There's circles around the wire, but they're vectors, so the direction of those circles is important. Like, are they clockwise circles or counterclockwise circles? If we had a wire, long straight wire, with electricity flowing through it, and a bunch of compasses, little dollar store compasses, we could bring the compasses close to the wire, and we could see which way the north pole of those little compasses twigged, and that would tell us the direction of the magnetic field around the wire. Luckily, other people did that for us. It's tricky to do. You have to have a large current and a pretty decent compass, but people did it, and then they figured out a trick so that we don't have to get the compasses out every time. They figured out a trick for how we can determine the direction of this magnetic field around a straight wire, what the direction of these circles are, whether it's clockwise or counterclockwise. It's a very convenient trick. The geometry of our hands will tell us the direction of this electromagnetic field. So it's called the left-hand rule and the right-hand rule, and we're going to have a second one soon, but it's for long straight wires. So left-hand and right-hand rule for straight wires. Here we go. At this point, take either hand and make it what I'm going to call a hitchhiker hand. So way back in the day when people didn't have a car, instead of calling an Uber, they'd hitchhike. They'd stand on the side of the road. Their hand would be shaped like this. That's what I'm going to call a hitchhiker hand. Just your thumb sticking out of your fist. When you do that, if you match your thumb so that your thumb is matching the direction of the current, remember we're talking about the magnetic field around a straight wire. In this orientation, your thumb is kind of straight. So have your straight thumb match the direction of the current. When you do that, then your fingers, which are curled in a circle, the curl of your fingers matches the direction of the magnetic field. Since there's two ways to think about current, we have to use our two hands. If we're going to do what we call the conventional current, the positive flow, then use your right hand. Take your right hand, have your right thumb match the direction of the positive flow through the wire, then your fingers are curled in the direction of the magnetic field. Or if we want to do negative flow, I don't have a graphic for a left hand, but you do the exact same thing, just use your left hand. Have your left thumb match the current in the wire, then your fingers are curled to match the direction of the electricity. It's awkward to type it and talk it, but here's kind of an example. Let's say we've got a straight wire and there's negative flow current in that wire moving away from you. I want you to figure out the direction of the magnetic field around that wire. Before I scroll down and show you the answer, we're going to apply one of those left-hand or right-hand rules. Since this says negative flow, we're going to use our left hand. Since it says it's a straight wire, I want you to make a hitchhiker hand. So take your left hand, make it look like you're hitchhiking. Now the last step is your thumb matches the electricity, so take your left thumb, take your left thumb and point your left thumb away from you. So articulate your wrist and your arm so that your thumb is pointed away. When you do that, look at your fingers. Which way, so you can probably see your pinky finger pretty good. Which way is your pinky finger curling? Would you describe the sort of direction that your pinky finger is pointing in? Is that pointing clockwise or counterclockwise? Spoiler alert, the answer is counterclockwise. There's the answer. Now this big monster document, there's a little sort of visuals to help with this. So this is just a typed up version of what I just did out loud. Negative flow, so we know you're going to use your left hand. It's a long straight wire, so make a hitchhiker. Here's my hand. I tried to point my thumb away from me. When I do that, look at what my fingers are doing. I'll switch tools. My fingers are pointing like that. Or added an arrow. If I extend it, the arrow looks like it's counterclockwise. Oh, the last step. Sorry, forgot about this when I answered in words. The answer is clockwise. Sorry. The answer is counterclockwise. To draw it though, like if we were just talking about this in class, you could say to me, hey, yo, it's counterclockwise. But since you're going to be having to draw this and hand it in, to draw this, you're going to have to draw the current, which was moving away from you. From what we talked about earlier, moving away from or into the page, we're going to draw that as a circled X. So the circled X represents the current, and then outside of that, need to draw circles that are counterclockwise. So in this case, the answer over here in this box, the answer is an X to represent the negative flow, and then counterclockwise circles to represent the magnetic field. I've typed up more examples with solutions. I'll talk you through one more, and then I'll turn you loose to work through these on your own. Let's say it's a straight wire, so we know we got to do hitchhiker hand. And this time I've made it positive flow, and the positive flow is pointing towards you. So straight wire means hitchhiker hand. Positive flow means we're going to use our right hand. And it says that positive flow is towards you, so put your right thumb towards you. So try and articulate your arm and your wrist so your right thumb is pointed right at your eyeball. If you could do that, take your right thumb and point it right at your eyeball. Which way are your fingers curling? Okay, the answer, I'm going to type it here, or write it here. Right thumb point at your eyeball. Your fingers are going to be curling counterclockwise again. Just the two I happen to make up first are both counterclockwise. If we were going to draw it, the drawing is going to be down below so you could scroll and already see it. But if we were going to draw it, we need to draw towards you or out of the page, and then counterclockwise circles around that. It's been a while, but a vector that's towards you or out of the page, if it's an arrow pointed right at you, you would only see, the dot. So this circle represents the current. Then outside of that, we'd have a magnetic field that happens to be counterclockwise. So draw another circle and put some arrows to show counterclockwise. Here is my typed explanation. Right thumb towards you, counterclockwise, draw it with a dot and counterclockwise around the outside. There are, I think, oops, don't want to give it away, one more example. So I'll let you work through that other example, example 3, see if you can match what I've typed up there. And then we've got a second kind of electromagnetism that we need to tackle next.